In video 45 of the Foundations of Computational Economics, we will talk about method of simulated moments and more generally about estimating economic models which are solved numerically. So the kind of a philosophical question is, after most of this course behind us, we have learned to write and understand Bellman equations that represent real life, dynamic choice situations as an economic model. We know how to choose an appropriate solution method from a whole range of methods that we looked at. And to solve the model, we've looked at how to simulate data from the solution of the model. So what do we do next? Why do we need all of these skills? And the answer that we sort of encountered already is that once we've simulated some data from the model, from the solved model, and here I'm assuming that the code is already debugged, we can study the implication of theoretical assumptions of the model itself, right? So that was the main reason to write the simulator in the first place, to understand what various theoretical assumptions that we put into the model setup actually imply. And we can also run simulations of the optimal decisions or maybe of optimal policies. But remember, all of these would be subject to particular values of the model parameters, like beta, for example, discount coefficient, or parameters in the distribution of shocks of random incomes in the consumption savings model, and things like that, right? So we could actually run some simulations and analyze optimal decisions for a range, for ranges of these parameters. And sometimes that's enough. Sometimes you can say that, all plausible values of parameters are within a particular region of the parameter space. And for all of these parameters, you can do a bunch of runs, kind of a Monte Carlo, with parameter distributed in that region, and conclude the same thing, and then that must be true for the real life as well. But the ultimate goal for this numerical modeling is to match the model to the actually observed data. If we do that, if we bring the model to the state where the simulations from the model would actually replicate the data that we observe in the real world, then what we can do then is we can quantify, put numbers on various effects of the model setup. So you can start saying things like this mechanism is more important. Mechanism might be or must be more important than that mechanism, or this effect is larger than this effect in real life. Now you can talk about real life. You can perform counterfactual experiments, and we'll talk a little bit more details about what it is, but it's basically simulating the behavior of the decision makers in the hypothetical situation. And more interestingly, we can start falsifying theoretical constructions, theories, basically, by saying, by observing whether a particular theoretical model fits the observed data. And that goes back to the Popper's falsification principle, where real science is made by formulating hypotheses and theories which stand only until they are falsified, and any theory which cannot be ever falsified is not scientific. So in that sense, doing numerical analysis is really making progress in scientific research. So the second approach that I just described is the subject of what's called structural estimation. Structural estimation is a field of econometrics which is centered around methodological development and applications of the approach, which is given by the following steps. We need a theoretical model of some behavior. We need to implement it numerically, and that's what has been the subject of this course. And then, given that implementation, we can formulate a statistical procedure or an estimator so that it would be possible to find values for the parameters such that the model, describes or matches the observed data in the best possible way. And so this is what structural estimation does, right? It takes an economic theory which has some parameters and finds the values of the parameters such that the theory matches the real world. And then, of course, it's very important to assess the variability of these values, of the parameters. So we need standard errors of estimates. That's what it says here. And, there's this long-standing opposition between structural econometrics and reduced form econometrics. Although with the appearance of fields like randomized controlled trials or control experiments in more general, and with the existence of causal econometrics methods like instrumental variable or regression discontinuity, and actually some applications in the machine learning, this boundary between reduced and structural econometrics is becoming more blurred. But what you need to know is, structural econometrics is a theoretical model which is directly taken to the data with direct estimation of parameters from the observed data. Whereas the reduced form modeling is usually requires also many assumptions, but these are more of a high-level assumptions coming from one of the more standard econometric models or setups. And then, a lot more emphasis is given to data analysis. Keeping that in mind, it would be worth saying that in structural econometrics, where this numerical modeling is needed, the identification of parameters comes from two sources, not only the observed data, which is more of an importance for the reduced form econometrics, but also from the structure itself, from the theoretical structure of the model, which essentially fixes the assumptions on causality that are embedded into the theoretical setup. And in case of the structural econometrics, these assumptions are usually informed by the economic theory and are based on the theoretical works in economics. Whereas in the reduced form case, they're usually higher level assumptions informed by the econometric principles. So because structural estimation has a foundation in the economic theory, that's what actually gives allows for the counterfactual simulations to be run. Because these counterfactuals, they not only are founded on the observed data, but also on some theoretical knowledge about the economy that goes into the results of the counterfactual analysis. And so here's how counterfactual simulations are done. First, we need to estimate the model using the observed data. And this is the subject of this video and the next video. So we need to find parameters such that the model matches the real world in some particular way. Then we can simulate data under the status quo, so under the policy regime that is in place, which was in place when the data was observed. But then we can also change the policy environment, and here's the structural econometrician has a complete freedom. Right, because we can, change taxes or change rules how pensions are paid out, or change unemployment policies or anything like that. And then we can simulate the decisions of the model decision makers in this new environment. And here I'm thinking about modeling the decisions of individuals, right, on how to consume and save or supply labor, things like that. So under the alternative regime, we can see how the decision makers behaviorally respond to the changes in the policy, and then comparing the two simulations reveals the effects of the policy. A really nice but seldomly done final step would be to quantify the uncertainty of these predictions using some methods from the uncertainty quantification literature. Now, why is this possible with theoretical foundations in the model or in the analysis? Well, the thing is that under structural estimation, we can formulate the theoretical model such that only the deep behavioral parameters are estimated and drive the behavior. So with this, we can uncover what's called deep structural parameters of the behavior. And by definition, what are these parameters? Well, these parameters are those which we can safely assume do not change when the policy is changed. So it's basically, parameters like risk aversion, which we can reasonably say does not change when the market structure changes, right? This is something that characterizes the investor rather than changes together with the fluctuations of the market. Or a parameter like a trade-off between leisure and income and consumption, right? That drives the behavior of individuals when they react to different policy scenarios or social benefit schemes. So these parameters that we can estimate with a theoretical model and are assumed to be policy invariant, and that means that we can simulate decision making in a different policy environment, just because these parameters would be the same. So this is something which is very hard, if not completely impossible, in the reduced form, sort of pure data analysis applications, because then it's very hard to separate the behavioral adjustments from the direct impacts of the policy itself. And what's usually uncovered are patterns in the data and the parameters which describe these patterns. But not these deep behavioral parameters. In other words, it's hard to claim that parameters that are uncovered in the data analysis applications would be policy invariant. Right, a couple of words that should be said about estimation or versus calibration of economic models. These terms are sometimes used interchangeably, and different fields of economic research tend to lean more to estimation or calibration, with, say, calibration is more popular in macroeconomic research, for example. Well, from my point of view, the two crucial differences are these. Does the study produce standard errors for the estimates of the parameters? So, does the study worry about measuring the variability of the estimation results? That's usually what's done with estimation rather than calibration. A second very important question that is addressed by standard econometric methods or statistical methods is the identification of the model. We have to make sure that only one set of parameter values can explain the observed data the best possible way. So it's impossible to find a different set of values for the parameters which would explain the data equally well. Right, so typically these two steps are not done in the calibration exercises, and it doesn't really matter. I mean, sometimes the calibration employs algorithmic search programs that explore parameter space in some way to find the parameters that best fit the data. But then, usually these two steps are not performed. And also, sometimes, you may think that calibration is basically fixing some parameters and finding values, optimal values for the parameters which are left free, and often it's actually is done in calibration where parameters are fixed at values, say, that come from previous literature, something like that. But it's also not uncommon that in estimation applications, some parameters are just kept fixed and not estimated. But then for the rest of the parameters, standard errors are calculated. All right, so here's a rough workflow of a structural estimation application. Everything starts with the theoretical model development. And in this course, we've looked at the models which are already designed and known. But in the actual research application, the model development is an extremely important step to which you may have to come back a few times, among the steps. Because the model, as we know, is the short and concise description of the process that the researcher is interested in, but it has to have all the mechanisms and details which are relevant for the studied question and try to assume away everything which is not important. So it's not a trivial task to just formulate the model. Then practical specification has to do with, what is the good way to implement this model on a computer. So implementation and specification, mathematical specification, theoretical specification can be helpful or less helpful for the numerical implementation. Of course, solving the model is the third step, and here the choice of a method and implementation of the code and debugging the code is very important. And it can take a lot of time just to develop the procedure. See, this is also what separates structural approach to economic modeling from, say, reduced form econometric approach, is that every time the theoretical setup every time is somewhat new and requires a separate implementation in the code. Right, so there is no standard collection of models that can be used. Although some efforts are done towards this direction, and the class Deaton that we have written in this course is an example of such sort of standard software code base for modeling consumption savings problems. The fourth step is very, very important, understanding how the model works. We'll talk a little bit more about it today, but after that, once you understand how it works, and that includes both making sure that the code is bug-free and that you understand how various parameters affect the simulated data that comes out of the model, then the estimation can begin, and that's usually numerically costly step, which actually performs the search for optimal parameter values, which should follow by validation. So, model specification tests and checks that the model is adequate to represent the data, and this is usually done with some sort of out-of-sample performance if it's of the model, if there is data to allow for that. And then finally, and most importantly, is policy experiments and counterfactual simulations. That's what this whole exercise is for. This is basically this whole 7 steps present a plan for a standard structural econometrics paper. Now, this is basically true for you to understand where the numerical economics fits in this work, and this is essentially solving the model and implementation of the estimation method. The concluding lectures in the course are designed to give you a better understanding of the importance and where this whole course is placed in the economic research. So, look, we've looked at the theoretical models in videos 35 and 39. This has to do with consumption savings model and various ways to solve it. The implementation, there are 2 long videos where we've implemented the initial methods and then the stochastic part of the or version of the model. And solving the model, this is also a long implementation video. Where we've coded up several solvers. Now we are at the stage number 4, understanding how the model works, and we will talk about estimation in this video. Now, if you're interested in validation of policy experiments and sort of adopting this workflow in your own research, please drop me a line, talk to me. Okay, here's the code that implements the Deaton's class. This is a copy from video 42, and I'm just going to run it, and we'll use the class as a module. Now, what is it to understand how the model works? Well, here's a simple algorithm. Solve the model for a set of parameter values, simulate data from the model. Does it make sense? We have to answer this question. and then repeat many times. Actually, a lot of time can be spent in this loop, in understanding how the model works. And let me emphasize that solver of the model and the simulator from this model should really go side by side. It does not make sense to analyze the solver of the model if you cannot visualize or somehow make it easy to check what the solver produces. And the simulations from the model is the best way to do it. Because every code has bugs. And every code requires debugging, and it's very hard to be absolutely sure that there are no bugs. This is like falsification of scientific theories. The code can be thought of being bug-free only until a new bug is observed and terminated. Right. So, if you see unexpected or surprising results, most likely there's a bug in the code, right? But once you are at that state when you believe that the code is bug-free and the unexpected or surprising numerical results or simulation results still appear, maybe you're making some good research progress, and maybe you're onto something which is publishable. So let's look at a few cases of our Deaton's model. Which, this is an illustration, an example of how you would go about understanding the performance of the model. So I'm going back to the Keynes test, right? The setting where the consumption should be completely flat in the deterministic model with the beta r equals 1. So this line sets up the model. Remember, if if we're using more than one quadrature points, then we actually are assigning an income of 1 to the decision maker, the expected income. Whereas if the number of quadrature points is 0, then we're replicating k-keying when there's no income. Okay, we're solving with EGM, of course, right? Once that we know what's the best way to solve the consumption savings models, then we are going to be using that. The initial wealth, just a couple of values here, and then we simulate the wealth and make some graphs. Now, does these lines make sense to you? Well, as we were saying, the simulated consumption paths here should be completely flat. And, it's nice to know also that the wealth is flat. Well, this is an infinite horizon problem. In a finite horizon, wealth would be declining until the capital T period. But in the infinite horizon problem, they look like that. And that's what we would expect, but let me just run it with one initial wealth. Does this make sense to you? Aren't we falsifying the conclusion that the model works? And, there's a declining consumption profile here. Well, look at the scale of the graph. This is declining, but it's basically almost down to the numerical precision. On the computer, nothing is absolutely perfect. But if we draw a couple of lines, and the only reason that we see this, it goes from whatever is number, the scale here is 10 to the minus 10. So this is a tiny decline. But if I say 75.5, for example, I'm drawing 2 points just to keep the scale of the graph fixed. Now it's the scale from 7.075 in consumption, right? Consumption is smaller than wealth. So in 1075 to 10755. So this is it's difference by a tiny amount, 5/10,000, and we're still seeing completely flat profiles. We could make the test harder by moving these points together, so decreasing the scale, and see it holds up with completely flat profiles for a good range. All right, another test. Deterministic model with r equals 1. So there is no return to saving. What's the optimal consumption. Does this make sense to you? So very fast people fall from both levels of 175 and 225 of the initial wealth. They very fast fall to the flat profile, which is 1, and the wealth is staying at 1, so they're basically relying on income. Well, income is deterministic, right? So it does seem to be making sense that in the infinite horizon, the optimal thing to do is to just fall onto income. But, let's try to change beta coefficient. Look what's going on here. It takes longer to fall down to this flat, hand-to-mouth regime of consuming just the income, and this is because the future becomes more important. Now, interestingly, here we have a bit of an artifact, right, where it's probably the number of grid points on the state space that creates this little step, and we may want to try to counteract it, say by doing this. Well, still remains, but you can see that the green profile falls faster to the standard consumption of 1, which tells me that these technical parameters are actually important. So here now we have a flat transition. Yeah, so you can see that we require quite a number of points to be able to completely make sense of these simulations. And so it's important to be aware that even with the best solution method, like the EGM, we are making some numerical mistakes when solving the model numerically. Now, 2 stochastic models with different income variances. So these 2 models differ in the value of sigma. And so in model number 1, the variance of the income, so the income shocks, is smaller, whereas in the second one it's larger. What do we see? And it's important to say that both of these models are simulated with the same sequence of random numbers, right? Because the seed is fixed. We can ensure that the models have the same shocks. It's just the variance which differs. And this is important when analyzing the simulations like that. Well, in the first model, wealth jumps, in the best positive shock, it's a little bit under 4. This is a little bit over 8. So we can see that the wealth profiles are different, but look at the shape. The shape is pretty much the same, right? And what about consumption? The shapes of consumptions are also pretty much the same, almost the same, right? Well, some lines are closer than here. And we can see that on the graph, but the reactions are exactly the same. That's because the preference parameters are all identical in these 2 models, all right? And so the magnitude of consumption is different, 1.4, 1.2. That's the same, but once we get into some nice situation like here, for example, it's 2.5, and this is 1.6. Right, so it's only the levels which differ, whereas the behaviors seems to be the same. That's what we would expect, I suppose. It's interesting to see what's going on actually on the bottom half. So when yellow goes down, like here, for example, the consumption is the lowest point is about 0.5, and here it's even lower. Okay, so it falls. Yeah, I guess it just falls together with wealth on the bottom and doesn't go as high as wealth on the top. But because wealth is falling, then that's the difference that we see. Okay, I think it does make sense there as well. And so here we're looking at 2 models again, which differ by the beta coefficient. And let's try to compare these profiles. 1.5 for sigma, so pretty large shocks. What's the difference between these 2 and these 2? Well, from my point of view, you can see that over here, wealth sort of comes down to pretty low levels all the time after a positive shock, like here, for example. Whereas in this example, it never really comes down. I mean, it does come down low after a series of negative shocks, but every time it goes up, and then it doesn't come down to the same lower level compared to this area here. And so that's the difference between the beta coefficients. Right, and that reflects what we saw in the very beginning, where it would take longer for the wealth to come down in the deterministic model without the returns to savings. So it's like larger beta makes the simulated consumption profile be flatter, and wealth profile as well. So that seems to be making sense as well. And I would say that, yeah, you know, these preliminary tests tell me that the model does make economic sense. There is nothing that I would intuitively object to. Okay, as I said, that process could go for a lot longer. So this is an example of analyzing the numerical results from the model. But once we've done that, we have seen how changing parameters is reflected in the changes in the simulated wealth and consumption profiles. And this is the property that is in the heart of the method of simulated moments. Imagine that we have some data on observed consumption and wealth, or some statistics, you know, some aggregate data on these variables. Then we can ask ourselves, you know, what are the values of parameters that we can put into the model such that the simulated data reflects the data that we observe in the real world. The data, or some descriptive statistics called moments, from the data in the real world. The origins of the method of moments are, method of simulated moments are, as you would think, in the method of moments and the generalized method of moments. And both of this have to do with the idea of directly matching the moments produced from the model, and this would be theoretical moments from the model, where a moment is a function of some random variables that are produced by the model. So the model would have some random shocks, and then, you know, the simulated consumption is in fact a random variable, a random process, which stems from the model under the optimal policy function. Right, so we solve the model and plug back the policy function back into the model and simulate from the model as if that was a Markov chain, kind of. You know, back in the video on simulations, which is where is it? 36. We talked about that. Okay, so here I wanted to say that there are theoretical moments which are produced by the model, and matching those is what method of moments and the generalized method of moments are doing. Whereas in the first case, you know, the number of moments to match equals to the number of parameters to estimate, and then the estimator is solving the system of equations of some sort. And with GMM, we are minimizing the distance between the theoretical moments and the empirical data moments. Well, the method of simulated moments is based on the observation that the theoretical moments, which correspond to the model, are sometimes and often hard to derive. And so instead of deriving theoretical moments, what we could do is we could just simulate the variables that would be needed to calculate this descriptive statistics, the models. So in other words, we're simulating the data which is similar to the data that we observe in the real world, and then we are calculating moments from both the simulated data and the empirical observed data. And here's the definition of the estimator. That's whatever minimizes the following expression, and this can be thought of as a distance or this criterion essentially combines different distances between the simulated data and the real data using some weighting matrix W, and each E is here a vector, a row vector of k moment conditions, right? So here we're using k different ways to try to bring together or to measure the separation between the simulated data and the real data. And this k is in fact k moments. Each E is a moment condition which we want to minimize, but to be able to compare different contributions of the different moments, we're using this weighting matrix W. So here is the structure of this vector of moment conditions. First of all, it's a vector of k conditions, right? And each of them is given by the difference between the moments. One is calculated from the data, and they're called empirical moments, and another one is calculated from the model and simulated, in our case, conditional on a particular vector of the model parameters. And so this whole vector of moment conditions becomes the function of parameters, right? And that's how the objective function of the MSM estimator becomes the function of parameters theta as well, and that we can minimize in some parameter space capital theta. Well, the theory of the method of simulated moments, I don't want to go deeply into. It's very well established. Here are the classical papers that establish consistency and asymptotic normality in several scenarios that you can go back to if you will be working with MSM seriously. But let me give you just a brief overview of this estimator. So as I said, the MSM estimator is consistent, and what's important is that it doesn't depend on the choice of the weighting matrix. What the weighting matrix really affects is the efficiency of this estimator, and it it is asymptotically normal as well. And this variance-covariance matrix in the asymptotic distribution is what is dependent on the weighting matrix that we choose. So here's the formula for the variance-covariance matrix of the estimate. So this tells us about how variable the estimates that we can compute are, right? So this is the foundations for creating or for calculating the confidence intervals and testing hypotheses. What are the components here? Well, the weighting matrix itself. Then we need the Jacobian of the moment conditions. So we are checking how flat the moment conditions are when at the theta, which should be a consistent estimate. For example, the value of theta that we converge to in the estimator itself. Now, when we are putting this gradient into the quadratic form, like here, then we get the measure of the curvature of the criterion function, and you can think of this as, if the criterion function is really is really flat at the point where it is minimized. That means that we don't have a lot of precision in the point where it's minimized, compared to when the criterion is really steep at the point where it's minimized. Then we know that this is fairly accurately pinpointed minimum. So that's the idea under the or that's the reason why this D matrix, the Jacobian matrix, enters the formula. Now the S is a variance-covariance matrix of the moment conditions. This is a theoretical one, which is not accessible, but we can estimate it using the simulations as well. And finally, tau is the ratio of the simulated to the empirical sample size. And here you can see that, the more we simulate, the less the penalty from the simulations itself is. And with the number of simulations in the method of simulated moments growing to infinity, the efficiency of this method becomes closer and closer to this normal GMM. the general method of moments. Okay, now the optimal weighting matrix. As you can see, by choosing the weighting matrix in the right way, we can influence the accuracy of the estimate. The asymptotic variance of the estimates is minimized when the weighting matrix is chosen appropriately, and the best choice is the inverse of variance-covariance matrix of the moment conditions at the true value of parameter. So at the true value of the parameter, and it should be also the expectation of the inverse. It's pretty impossible to find, but if it is chosen optimally, then the formula for the variance-covariance matrix of the estimates themselves becomes a lot simpler, and this is what often is used as if the weighting matrix was optimal. And then the weighting matrix itself can be estimated from the variance-covariance of the moment conditions calculated at some consistent estimator. And that, gives this iterative structure, or sort of the closed loop structure of the estimator, because in order to know a good weighting matrix, we already need to have the moment conditions computed at some consistent estimator. From this, several procedures had been developed where you would estimate, you would get a consistent estimator with some simple weighting matrix, for example, just the identity matrix, and then re-estimate, after updating the weighting matrix. But the bottom line is that because we are getting consistent estimates with any weighting matrix, in practice a whole variety of them are used. The simplest is just the identity, right, where we don't prioritize any of the moments. Diagonal weighting matrix is usually preferred to the full weighting matrix because of the small sample biases in the estimation of the variance covariance. Now, manually chosen weights are sometimes used to bring all of the moments to the same scale. This is unless the moments are measured in relative terms. Now, using sample variance, if the observed data is not aggregated, if the observed data is microdata, then we can measure the variance of the moments in the data itself and downgrade those moments which have large variance and which are thus measured not very well. We can estimate the weighting matrix from the moments conditions according to the formula on the previous slide, and then form some sort of an iteratively updated matrix. Two-step is quite common. Now, there is a newly robust estimate for the weighting matrix, which you can look up in the books. And sometimes additional adjustments are used that come from the model structure itself. So there are very many different ways to do it. Now, choice of moments is another question, which is kind of more art than science. Which moments to choose to estimate your model? Well, usually there is some tradition, right? Then it is also what you're interested in when creating the model. So that would be sort of part of the theoretical development of the model that dictates you which moments you want the model to absolutely try to match as best as possible. And then, when going through the step of understanding how the model works, it is also very clear, or it should be very clear after this step, that you understand what features of the simulated data change under the changes of various parameters. Like, for example, right, we changed the sigma parameter in the distribution of random incomes, and we saw one change in the simulated data. And when we saw a completely different change in the simulated profiles when we changed the beta coefficient. So in order to be able to pinpoint the parameter values, the moments should be based or somehow related to these changes that are induced by the changes in the parameters themselves. So the moments should adequately represent the variation that is due to the changes of the parameters. Now, all in all, MSM is a really versatile and commonly used estimation methods. It is not data hungry, or not as much as, say, a method, the maximum likelihood that we will be talking about in the next video. It allows to combine different data sources. It doesn't rely on the distributional assumptions as much. It relies on the moments that are, of course, subject to the distributional assumptions, but not on the complete shape of the distributions. But it lacks in efficiency, and the weighting matrix is often simplified in practical applications, make it less efficient. And still, this is a very widely used method in applied research, and definitely not that hard and suitable for many different models. So in order to do a little illustration, let's consider the following setup. First, we will solve the model, the Deaton's model, and we will actually simulate some wealth data from the solution of the model and treat it as if that was observed in real life. So we draw initial wealth, and you can see I'm fixing seeds everywhere to make this calculation repeatable. So we're simulating, and the data on wealth is going to be just the stream that we simulate. So we're going to use this data on wealth as if it was observed. Okay, so what are the components of the method of simulated moments? If you go back a few slides, you would see that the moments functions, the moment generating functions, is something that we need to specify. And this function will compute a couple of moments, means and standard deviation from the tail of the given time series, and it will return it as two separate outputs. So it gets data, and then it computes along the last axis. It computes the mean and the standard deviation of the last so many observations, right? This is a slicing that includes the parameters, so 10 by default. This is model generating function that is mentioned right here. And we're generating all k equals 2 moments in one here. Okay, so now that we know the moment generating function, we can calculate the data moments. We have 50 individuals in the data observed for 61 period, but we will be using only 10 last periods for the calculation of this distribution of these 2 moments. And here so what are we trying to match, right? We're trying to match the expectation, the mean, and the standard deviation of the wealth distribution simulated in this infinite horizon stationary model. So here we are calling the moment generating function with the data on wealth that we have. And I'm computing the mean and the standard deviation of the moments themselves. So if you forget about for a second, then first moment is the mean and the second moment is standard deviation, and just think of them as first moment and second moment, then we can calculate the mean of the first moment and the standard deviation of the first moment that we observe in the data. And we print them out, right? So here for moment 1, which is the mean of the wealth distribution, the mean is 6.15 with standard deviation, which is pretty large. And the standard deviation of wealth, that's the mean of the standard deviation across people in the that we observe, is 2.07 with also a pretty large standard deviation. Now, I also want to form a vector, an NPy array vector of the means of the moment, which we will use in the estimation. We will try to match the means of these 2 moments. So we're trying to match the mean and the standard deviation of the wealth distribution, and thus we are trying to match the means of the 2 moments. How do we do that? Well, we set up the model, and that's going to be a Deaton's model. We fix the seed to make everything repeatable. This is convenience, but it's going to be important, extremely important, in just in a second. We have the initial wealth distribution and the identity weighting matrix to start with. Oh, we're actually not using this, but okay. Right. So what are our model moment conditions? Moment conditions, remember, this is a vector of, this is the vector E of moment conditions. This whole vector, which includes the differences between the data moments and the simulated moments. Well, to calculate the moment condition, this is going to be a function of theta. Theta, in our case, is just beta. We're only estimating one structural parameter, beta. Again, we fix the seed, and this is important here, extremely important, because when we change beta, we don't want to observe any changes which are due to the different random numbers being used in the in this criterion function. We want these random numbers to be fixed once and for all for the whole simulation, for the whole estimation. Then we solve the model using EGM. We simulate data from this model using the initial wealth, which comes from here. For, say, 60 periods, we don't plot. And then we calculate the moments, the C moment 1 and C moment 2, from the moments generating function. Right? And then we return the difference between the simulated moments and the moments in the data. But think about this. This data moment is just an element of a vector. It's a scalar. But the C moment 1 comes directly from the moments function, which is applied to the whole time series. And not only time series, this is actually a table, right? Because we have 250 people simulated for 60 periods. So this is panel data. And so the moments function returns a whole vector of moments, sort of one for each simulated individual. This is going to be important. So we should remember that the return from the moment condition is a vector of individual specific moments. Okay, and here's the main code to run the estimator. I'll need to switch to the notebook view. It runs the estimator. It depends on the data moments that we calculated from the observed data. The moment conditions function that we just coded up. Weighting matrix, and it's by default it's just an identity matrix. Now this bracket is for convenient search of the optimal parameter. And this is what's needed for the Brent here, for the Brent optimization algorithm that we are using. And we are also using these brackets to make some plots. If plot is true on the input argument. Now, there are two internal functions here. First function returns the mean of the conditions. It calls the moment conditions function that is passed into this run MSM. And it converts the tuple of the returned moments. So the moments are returned as a tuple of lone vectors, individual specific moments. So we're creating a matrix out of that, and then we take the means among all of the individuals. So the mean conditions returns the means across all the simulated individuals. Okay. Once that is done, this is used in criterion. Then we can form the actual criterion of the MSN. We have to do this all sort of part by part here to be able to calculate all the matrices that are needed for estimating the variance-covariance matrix of the estimates. Okay, then here's the default weighting. And then here's the main work, right? We're minimizing the criterion function of the MSN estimation method using Brent. There are some arguments that the criterion has to get, which is the weighting matrix, the additional arguments, brackets, and the tolerance is 10 to the minus 8. Hopefully we succeed, and then the theta hot, the estimate, the MSM estimate is taken from the res.x. Of course, this code only works for the scalar parameter, and in more general form, it will allow for a vector of parameters in this minimization, and would use a different minimization method, not just a scalar minimization. So this is just an example. Now, I did not pass the number of simulated individuals into this function, but we need it. And so the easy way to check that is to calculate all of the moments, say at the estimated parameter, and calculate the length of, say, the first moment that we've calculated. So the moms is a tuple of different moments, and each element of this tuple is a lone vector of, taking the length of that vector gives us the number of simulated individuals. We need that because we need to have this constant term, and I'm assuming here that data only had one observation, which is not true, but still, just to simplify. Now, D is the Jacobian matrix of the moment conditions. And here we are passing the moment conditions, this function that we've created that calculates the difference between the data moments and the simulated moments, but takes the means over all of the individuals. Right, that's the part that goes into the criterion function after all. But as a function, but we need the Jacobian of the moment conditions, and this is the convenient way to do it. Right, we are using the numerical derivative module from the SciPy MISC, and that just calculates numerical derivatives for us and returns a matrix D. Now, because we are only working with one parameter, then we actually need to check whether this is a scalar or not. This dWd, or it should be d transform wd in the matrix sense. But since we're using this matrix multiplication, then the vectors are transposed automatically. Right, and if it is not a scalar, then we apply the simple formula in matrix notation. Otherwise, we can just divide by the scalar dWd and calculate the standard errors. Given the standard errors and the asymptotic normality, we can calculate the confidence interval here, make some outputs, and make a plot. So here's the code. So let's run it. And before we look at the result, we are estimating the beta coefficient. The only thing, the true value of the beta coefficient is 0.92. That's where we generated the data. That's what it was. And here's the output from this run MSM procedure. You can see the graph of the criterion function, and it is minimized at the point 0.92092, which is fairly close to the true value of the parameter beta. The standard estimate is here, and the gray area on the graph. This is a two standard errors confidence interval that gives us the sense of how far off we are from the numeric value of the estimate, or how far off we may be from the true value of the parameter. So the combination of the estimate and the standard error, that's what makes this a real estimation exercise, as I mentioned before. Okay, this is using the identity weighting matrix. What would happen next, or what we can do next, is to resimulate the moment conditions and calculate the variance-covariance matrix of this moment conditions, calculated at the consistent estimate that we just obtained with the with the identity weighting matrix. And then we could, inverse this variance-covariance to get an updated matrix. But and here's what happens if we do it. If we do it, then the standard error of the estimate is still pretty close to the true value, but the standard error actually grows. Right? So why is that? Well, this is basically, this is unexpected. We would expect the better weighting matrix to produce smaller standard error around the around the estimate. But so here we are suffering from, from the fact that we are relying on the asymptotic theory, whereas we are having a small sample that we are working with. And so, in this case, it didn't help to run an iterative procedure. However, these are the steps that you would run in the more elaborate application. All right, so this is the method of simulated moments for you. I've put into the further learning resources, the references to the textbook for MSM. There is a notebook by Rick Evans on the method of simulated moments, which is part of the notes CompEcon. That's worth checking. He goes into further details about the possible ways to define a weighting matrix. This here is an example of the practical application, and this is my recent paper with Michael Keane, actually, to analyze the effects of the Australian age pension. And we're using method of simulated moments with some non-standard weighting matrix in there. Now, there is a lecture, going back to the more philosophical discussion of the structural estimation. There's a wonderful lecture. It's about 1.5 hours that Professor Keane gave at the Becker-Friedman Institute in Chicago on sort of life around structural estimation. And if you want to refresh your Popper's falsification principle, here's an under 2 minutes video on that. All right, see you in the next video.